Sara, over to you.
Yeah. Hello, everyone. Thanks for having me here. Uh, can you guys hear me? Okay. It's an honor to be with you here among some of the top people in this industry. I was so excited to share the work that me and my colleague Alice have been doing at King in the past years. And I can't see if you guys are falling asleep, but I will try my best to sound as interesting as possible. So today I'm going to talk about an interesting idea that ended up being a tool for automatic testing of King games. And we called it BATE. It stands for Bot for AI-powered testing. But first I'm going to give you a short intro about King. Then we can go through the cool stuff. So King is a mobile game company founded in 2003. It has made over 200 games since, and we are approximately 2,000 employees working in 10 different locations across the world. We have had something around 200 million monthly active users in the past quarter, and we have been acquired by Activision Blizzard since 2016. These are some of our major franchises: Candy Crush, Farm Heroes, Pet Rescue, Bubble Witch 3, and some of our QA roles: Agile Testing Lead, Exploratory Tester, Quick Regression Team, Test Automation Engineer. And our hope is that our bot, BATE, can help ease the work of people, some of the people working in these roles. Yeah, that's the hope. So let's see. What is BATE? BATE stands for Bot for AI-powered testing, and it all started with an idea of making a bot inspired by human testers that can explore the game and can map the graph of the game as it explores it. Something that can see the game and can test the visual aspects of the game. And it is working almost like a black box, so it doesn't really care about the underlying code, and it's kind of only through what it sees from the game. And its purpose is to help with manual testing, the tests that are kind of hard to automate using traditional approaches. And one of its biggest advantages is that it's pretty easy to scale. I mean, you can have like multiple instances of it running. It's not like humans testing that has like limitations. So you might now, yeah, I was actually clicking on the keyboard. It doesn't work. You might ask, why do we even need AI for this? Well, it goes back to the initial idea that we wanted something that we can apply to many of our games. Because if you work in a company that you have multiple applications or games that like have similar functionalities, you will notice that you have to make similar test cases for them. So we were thinking maybe we can like make a bot that can help us avoid these duplicate test cases, and we can use it for all the games. And the second reason is that using AI, we could get this flexibility toward the changes that happen in our games. Like, for example, in Candy Crush, one of our biggest games, we have like weekly or bi-weekly releases. So the test engineers have to like go through all the test cases and make sure that everything works. But like we were thinking that maybe we can have something that doesn't need these checks. And yeah, again, I clicked on the keyboard. And now the interesting part, how does it actually work? Well, to put it in short, it explores the game by taking a screenshot of the game scene, and then it tries to perform some sort of visual verifications using computer vision techniques. And by which I mean that it tries to see if it finds like any UI related bugs in the game screenshots. And the most important part is that it uses AI to find button coordinates or like interactable areas in the screenshots of the game. And then it tries to interact with the game. And for example, it tries to click on a coordinate or a button. So basically it explores and verifies visual aspects of the game. And now I'm going to give you an overview of the main loop that the bot takes in each exploration round. So it starts by taking a screenshot. I will just bear with me because I will explain each of these steps in more detail in the future slides. So I will just try to go through them quickly here. After taking screenshot, it inputs that screenshot to the next module, which is called image similarity module. And here we're trying to compare this current screenshot with all the formerly captured screenshots. And we're aiming to see if we can find a similar screen, which means that the bot has seen this screen before because it finds a similar one to it. And if it doesn't find a similar screen, it means that this is a new screen that we're facing. And the result of this module is particularly important for the next module, graph building module. Here we're trying to actually make a graph of the game, and in which the nodes are screens of the game and edges are the actions that take us from one screen to another. Here, when the image similarity decides if we are looking at a new screen, then it can be added as a new node to the graph. Otherwise, the graph doesn't change. Then we go to the next module, which we call UI analysis module. This is kind of like the most important part. We call it the brain of our bot because it has like all the machine learning stuff here. So the most important thing that we do here is that we process the screenshot using machine learning techniques to find interactable areas. And also we try to classify the screenshot into different categories. I will go through the details later. The result of this is a list of available actions that the bot can take. And then it goes to the action selection strategy, which chooses one of these actions and then it performs. After that, we go through the animation detection module. And this is basically needed because sometimes when we interact with the game, like for example, if you click a button, the game goes through some sort of animation phase until it gets to the next screen. So we needed some way to know when these animations are done and we can move to the next iteration and we can start taking the next screenshot. Yeah, so that's basically why we needed animation detection. And now I'm gonna go through these three modules and explain them in more detail, starting with UI analysis module. As I said, it has like different parts. Part one is the part that we use for detecting interactable areas like buttons in a screenshot. For that, we use the special kind of neural networks, which is a machine learning method called mask RCNN. I'm not gonna like go through how this works, but just try to explain it in like simple words. So it has two stages. In the first stage, it takes in a screenshot or like an image, and it tries to, using a feature extractor network, it tries to find a manageable number of regions in that image called regions of interest. And then this part returns a feature map of all those regions. And then in the second stage, it tries to predict the class, the bounding box, and the mask for each of those regions of interest. So as you see in the image in the left, it shows like a screenshot of the game, and it's just showing some boxes around the buttons. This is kind of the output that we get from this network. We also get the mask, but only the bounding box would be enough for us. So if you're looking if you're interested into knowing more details about like how you can actually implement this, how you can use such a network, I have added some like sources in this slide. I don't know if you will have access to the slides later, but there's like plenty of material out there. You can just like go to TensorFlow website or like a lot of other materials. So in order to train a model using this algorithm, we had to collect a lot of training data from multiple games. And the training data are basically screenshots that we collected from games, game screens. And then we try to apply some color and size augmentation to increase the number of this training data. And we manually labeled them. And by labeling, I mean we specified the button areas and interactable objects in the screenshot using a mask, by specifying a mask on them. And then we also use transfer learning. It's a technique where you can use a pre-trained network that has been trained on maybe irrelevant data categories like cats, dogs, cars, etc. And you can add your own data on top of it and use it for your own specific problem. Using this technique, you can actually transfer the knowledge learned by the pre-trained model to your own problem, and you can basically fine-tune it by adding your own data. It's particularly good when you don't have as much training data as you might need. You can use this technique. This is an example of a training data. Just wanted to show you that, we have this screenshot, and then we just specified a mask on the buttons that we can see in this screen. And the next module that we have in the UI analysis part is called game scene classification. And in this part, we are basically given an input screenshot. We can classify it into different categories. We need this part because sometimes in certain game screens, we don't need to start detecting buttons and clicking them. We need to perform different type of actions, not just clicking. So we needed to know what type of screen we are in, so we can basically perform the suitable action for that screen. For example, in the image in the right, I mean these the images that have the candies, like the game levels. Maybe we don't want to actually start clicking on the candies because nothing will happen. You need to like swipe the candies, and this is like one of the reasons that we needed to know what type of screen we are in. Basically, I need to add something here. Basically, we don't play the games. Our purpose with this bot is that we can test the functionalities around the game. And the reason is that playing the game needs a whole different logic. So it was kind of our decision from the beginning to separate these two. And we found a way to kind of bypass playing the levels, so we can get out of the game screens and try to progress to the further screens of the game. And I will get back to this later. I will explain how we actually do that. Yes, so in this game scene classification module, we also used another type of neural networks called MobileNet V2. You can find the implementation of it in TensorFlow library. It's pretty easy. So I'm just gonna explain how it works in very simple words. It works in 4 stages. You input an image, it tries to expand the number of channels in that input image, and then in another box, which is called like depth-wise layer, it tries to apply filters to the data and make new features out of it, features like edge detection, color filtering, and etc. And then it tries to compress the data to make it small again, and after that it takes the 3D small image and try to convert it to a 1D array so it can predict the class of that image. So this is like how it works simply. And the next module, I think I want to add something. So here also we follow the same approach for training. We collected like screenshots, put them in different classes, and also used transfer learning here as well. So the next module is image similarity module. So as I said, we needed a way to compare 2 images or like one image with a group of images to see if we find a similar image or not. And so we can know if we have seen this screen before or not. And for that we use a combination of 2 similarity algorithms. One is called perceptual hash similarity and another is text similarity. And now the perceptual hash similarity is just a hash similarity algorithm that, given a screenshot, it returns a hash string, which kind of represents encoded version of that image. And this particular algorithm also takes into account the features. It works in the feature level rather than pixel level. So given 2 images, you can get like 2 hash strings, and then you can easily compare the hash strings using, for example, Euclidean distance, and the result would be a similarity score. And the second part of this similarity, as I said, we use text similarity. For that, we used the Google Vision API text detection feature. And so with that, given an input image, you can get all the text from that image. You can extract this text from the images. And here I just put like some lines of code to show you how simple it is to work with it. You can just like create an image annotator client, and then you convert your image into the vision type image, and then you call the text detection function, which will return the text that it extracted from that screenshot. So pretty easy to work with. And now you might ask, why do we even need the combination of 2 similarity algorithms? Can't we only rely on hash similarity? That should be enough. But the answer is no, because there are cases like you see in this slide that they look pretty similar, but since they have been accessed from different parts of the game, they have like slightly different backgrounds. So if you look more thoroughly, you will see that in the dark area they have different pixels. So if we only rely on the excuse me. If we only rely on the perceptual hash algorithm, we won't be able to confirm that these 2 are actually same game screens. So we decided to add the text similarity to it, because as you see, these 2 have exactly the same text. And by adding that, we are able to confirm that these are actually the same screens and avoid having duplicate nodes in our graph. Yeah, the next module is called graph building module. And here we basically try to create a graph of the game as we explore it. So we update this graph. And in this graph, nodes represent screens of the game, and edges are actions, which can be clicking a coordinate or winning a level, and etc. Now I'm going to actually tell you how we capture screenshots and how we perform different actions. Easy. We have some sort of web servers inside our games, which we can interact with. For taking screenshots, the bot simply sends a request to this endpoint, screenshot, and it takes a screenshot of the current scene. For click, it's click a coordinate XY, and the win command wins the current level that we are actually in, and the lose loses the current level. And this is where we need to know what type of screen we are in. So if we are in a level, like the level that candies are in and you can play it, then we need to perform win or lose actions. So for now we only have these actions, but we are planning to add like more actions like swiping and etc. in future. The next part is animation detection part. And as I said before, we needed to know when animations are done, so we can start our next iteration. And for that, we used some of the functionalities in OpenCV library. It's a library for computer vision, and it's open source library. Basically, we took the frames of the game. We tried to apply some background subtraction to the frames, and that will give us, after applying this background subtraction, you might need to apply some filters to the frames to smoothen things out and to remove the noises. And that will give us a black and white image in which white pixels are foreground pixels and black pixels are background pixels. And then by counting the number of white pixels, you can know how many foreground pixels you have, and then you can like calculate the percentage of foreground pixels to the total number of pixels. And the reason behind that is that when the game is animating, so it's transitioning into like the next screen, if you notice, you will have like a lot of like the number of foreground pixels will be larger than usual than when the screen is static. So this is how we actually detect animation. We calculate the number of foreground pixels, and if they are larger than a threshold, then it means that it is still animating. Otherwise, it means that it's static. And so this module notifies the bot about the animations. Now I'm gonna go through some of the use cases that we currently are using with the bot, or we're planning to have in future. So this was an overview of the bot, and it explained how it is able to explore different parts of the game, and it collects information and saves it in a graph structure. And so while it's doing its exploration, as I mentioned in the UI analysis module, we also perform some visual verifications, like UI related verifications. So one of the use cases that is not UI related, that we kind of get for free, is crash detection. So as the bot is exploring the game, automatically it is able to detect certain crashes if they happen. And but the rest of the use cases in this list are mostly UI related, and I'm gonna show you using an example. So the first one is missing texture. It's an issue that happens in some of our games, that it can happen randomly anywhere in any game screen, and it is pretty hard to detect using like automation or like manually, because you don't know where and when and how they can happen. But they have this characteristic that they show, it shows itself using like with this pink color. So when a texture doesn't load properly in the game for some reason, you can see this pink area showing in the game screens. And for detecting this type of UI bug, we also used OpenCV library. We thresholded on that specific color. We thresholded the game screen on that specific color, and then we tried to find contours in that filtered image, and we calculate the area of the contours. And if that area is larger than a threshold, then it means that this screen potentially has a missing texture in it. And the reason that we are thresholding is that because sometimes we have like shadows around some other objects that might have the same color, but if it's like larger than an amount, then it's potentially dangerous. We don't want that. The next example is finding missing text, a lot of textures, missing text in the games. And this happens when certain text doesn't load properly in the game. And the good thing is that they usually are bounded with double brackets, so it's pretty easy to find them, because we have the ability to extract the text from the screenshots using Google Vision API, and we only need to search for these double brackets, and then we report them as a potential missing text case. Another example that the bot can also perform or do is looking for overlapping text. Sometimes when they translate the game text into different languages, the text might go out of its button border, or there might be some overlapping text in the game. And for this part, for the part that the texts are out of their button areas, it's pretty easy to detect since we have a bounding box around the buttons, and we get that from our button detection algorithm. Sorry, I need to drink water. And we get another bounding box around the text area, which we get from Google Vision API. It returns both the text and the bounding box around it. So the only thing we need to do is to check if they are overlapping or not. Another example, which is pretty hard to see, is some rendering issues. So if you pay attention to this image, you can see there are some like sparkles in the background, and they are not supposed to be sparkly. They are supposed to be dark because they're in the background. But for some reason, for some rendering issue, this happened. And this is also easy to do using like color thresholding algorithms. Yeah, this is like another example that we can do. So, and finally, the interesting part. So this is a video of the bot running on Candy Crush Saga, one of our biggest games. So you will see two windows. The window in the left is the game, and the window in the right is just the image viewer that shows the detected buttons with a box around them. And yeah, so please play the video. Yeah. Oh, no. That's the cool part. Cool, yeah. Yeah, so the game is in like fast mode, so it's like our game characters are just moving so fast, but it's just because we increase the like frame rate. And you can see that it sometimes finds boxes around objects that are not buttons, but that is okay because when it clicks them, it compares the screenshot before and after clicking, and it noticed that, okay, nothing happens because these two are the same. So it means that this wasn't a button. And if the screens before and after clicking are very different, then it means that it was a button. So it only saves the areas that it figured out that was a button. Yeah, so this will go on for a while. You can enjoy the performance of BaitBot for a few seconds. Oh, it's finished. Okay. Cool. Okay. Yeah, that was all. Thank you so much for listening to me. And I hope this presentation gave you some ideas or inspired you in some ways to consider using AI techniques as a complement to your efforts for automation. And please feel free to contact me after this session if you had any ideas or any questions, or you wanted to discuss this further. Just contact me. And if you're looking for a career, please take a look at our career website. Thank you so much, and I'm ready for questions.